Okay, so when we're talking about a graph, what we're talking about is vertexes and edges. In other words, we can represent different locations with this. So the black circles or ovals that you can see there, they're called a node or a vertex, and we can refer to them as vertices in plural. And then the lines between them we can call a line, or an edge is the correct term really to use. And you can see that what we've created then is the ability to link between different elements. So York is linked to Leeds. We have different types of graphs. This is an undirected graph, so you can see that York to Leeds, you can go in either direction. And again, from Leeds to Bristol, you can go in either direction. And it's just represented with that straight line between them. We can also have a directed graph. So in this case, you can see that York can get to Leeds, but you can't get from Leeds to York. And then from Leeds to Bristol, backwards and forwards, you can do. And again, you can go from Carlisle to Bristol, backwards and forwards. We can also weight a graph. In other words, we have a cost of getting from one location to another. So you can see from York to Leeds, it's 5. From Leeds to Carlisle is 3. And then from Carlisle to London is another 3. So in other words, 5 plus 3 plus 3 is 11. To get from York to London, therefore, would come at a cost of 11. That number is just a number, to be honest with you. But we can use that number to therefore just represent anything we want it to. It could be time, fuel consumption, distance, anything we wanted. But generally speaking, we are just referring to it as a number on its own. We obviously can have an unweighted one as well, and therefore there is no cost to travelling from these places, but we must still follow the routes of it being directional. So we just have some key names here. So we have an unweighted graph that is directional. We can have a weighted graph that is directional, and we can have an unweighted undirected graph or an unweighted directed graph. So we've got all these various terms. You need to make sure you're clear about which is which. To create a graph, we can use an adjacency matrix. You can see here that the row is dominant and the column comes second. So in other words, from row A to column B would be a cost of 5. And what that does is it dictates the direction as well in doing so. So we know that to get from A to B, in other words, from York to Leeds, will come at a cost of 5. And that matrix, therefore, represents the entire thing. Because this is a knowledge sprint, I'd perhaps recommend pausing this and just making sure you're fully clear about what's going on. We can represent an undirected graph as well, and an unweighted graph in this format. So you can see that 1 has replaced all of those different numbers. And because it's bidirectional, you can see that we can get from A to B at the cost of 1 and B to A also at a cost of 1. We can represent graphs within a list as well. So this is called an adjacency list. And again, this gives us an indication of what's going on. This is weighted to use these curly brackets. So from A to B comes at a cost of 5. We can't get anywhere else from A. From B, you can see it doesn't say A next to it, it only says D and E. So we know that from B, we can only get from to D or E. And again, we see that comes at a cost of 1 or a cost of 3. If it's unweighted, you use square brackets, and you can see the only real difference is that the numbers disappeared. And again, we can still see that there is direction being represented here. Okay, usage of graphs then. A graph can be used for depth traversal, or depth first traversal, sorry. And what we mean by that is literally how you move around a graph. So with depth first, we use a stack. So hopefully you've already watched the bit earlier in the video about a stack. If not, go back, find that, make sure you understand what's going on. And what also happens here is that depth first is recursive. And in other words, what we're doing is we're going along a pathway until we hit a dead end. So we're going to go from A to D, that's a dead end. Or we can go from A, B, E, and that is also a dead end. There's no reason to start from A, purely that it's in alphabetical order. So might as well, you know what I mean? We could have picked any other letter though. So unless the exam question states, you're free to choose. They often probably will state just so that they can get more consistent answers. So in other words, what's happening here is we start at A is added to the stack. We then go to D, D's added to the stack. D's the end, so we can't go any further. And therefore we pop D from the stack and return to A. We then go along a different pathway. So we're going to go B, B's added to the stack, C's added to the stack, C is the end. Therefore, we need to backtrack now. So we're going to go back to B. Is there any other path to take from B? There is, and therefore there's E, and therefore we've now reached the end. But what we need to do then is pop these from the stack so we know that we've fully completed the graph. So we're now going to remove E. There's no more nodes from B. We then go back to A. There's no more nodes from there. We're completed. You can see therefore we visited the A, D, B, C, E as our order. Simple algorithm here, so we start from whichever is our first node, we're going along till we reach the end of a pathway, and then we return visiting any nodes on our way back. Another alternative way of traversing a graph is a breadth first traversal. So again, we don't need to start at A again, but I will do just for sake of argument. But what's different now is that we're looking at the two adjacent nodes to any one node. In other words, you can view this as a little bit like levels, so that if you notice from A, both D and B are only one distance away, whereas E is two nodes away from A. We use a queue in this case now to traverse the traverse the graph, and therefore I'll demonstrate that now. So again, we have a head and a tail. Our head starts at A, we then add in both B and D into that. There's no reason why I did it A, B, D, other than it's just alphabetical order and therefore feels logic to, but I could equally have written A, D, B. Okay, the tail has moved across. What that means then is I've completed A. I then move across, because B is the next in the queue, I therefore visit B. We then add both C and E again to that queue. And again, I only added them in that order because that was alphabetical. There was no other logic applied. It could have been E, C for all it matters. There's nowhere else to go from B, and therefore we move along. So our head pointer now will point at D. Our tail is still pointing at the empty space. There's no more actual to add to this. So in other words, once we reach the tail, we'll know we've completed the entire graph. We now go to D. There's no more to add, and therefore we move on. Now to C in the queue. And again, we'll then move on to E in the queue. We've reached our end. The head is now matching where the tail is in position. We know we've completed the full graph. So in other words, we're starting at our first node, whatever that has been designated as. We then are visiting its two nearest and then moving along. We use a queue, as I've just demonstrated, to do so. Okay, well, I just wanted to say thank you for watching. I really hope you found it useful and really hope you've learned something. Please do like and subscribe, and I'll hopefully see you again. Thanks a lot. Bye.